In the last video, we talked about Boolean algebra, where we had all these rules and properties, which are similar to the mathematics that we're used to in algebra, but there are some new rules that we need to concern ourselves with. For example, one of the interesting properties is in Boolean algebra, you have a times a is equal to a, or conventionally, you might think that a times a is equal to a squared, as we're all used to, but that's not the case in Boolean algebra. Similarly, you may think that a plus a equals 2a, as it does in the algebra that we're familiar with, but we don't care about that algebra, so we say that a plus a is equal to a. And at the end of the last video, we expanded a function, given by this function here on the left. We expanded it in 3 terms. Now you may ask yourself, what's the point of this? Which I think is a very valid question in all of engineering. So that's what we're going to ask. What's the point of expanding these functions? What do we get out of it? So we're going to consider an OR gate, where we know that the truth table is given here on the right. And we know that the function of an OR gate is given as a plus b. Well, let's try to expand this as much as we can. And to do this, we're going to use the property of a plus a prime is equal to 1. So we can express that original function simply as a times b plus b inverse, or sometimes you will see a prime instead of a bar to represent the inverse. I tend to stick with the bar. I think it's easier to see. But continuing on, we'll have b times a plus a bar. And this term is equal to the term above. So now we can just distribute this out to say that f is equal to ab plus a b bar plus ba plus b a bar. So we've expanded the OR gate as far as we can. And what do we see from this? Well, if you take each input and you consider the barred term to be a 0 and the unbarred term to be a 1, what can we see? We get that f is equal to 1, 1 plus 1, 0 plus 0, 1. And this is kind of interesting because if we relate this to the truth table, you can see that all of these combinations are where we get our 1s. So what does f tell us? It tells us where the 1s on the truth table are. Now let's consider the AND gate. For the AND gate, here's our truth table. Our function is given by AB. And this is a lot easier because we have a similar convention to what we did with the OR gate, where now we can make the same kind of substitution. Have a 1 and a 1. And you can see the 1, 1 is there, and that's where we get our 1 output. So f tells us where the 1s are. Let's look at the inverse of f, though. It's going to be equal to AB, that whole thing inversed. From that, we can use De Morgan's law. Simply have a bar plus b bar. Now we're going to expand this. And what we get is that f is equal to a bar b bar plus a bar b plus a b bar. And from that, we would have a 0, 0, 0, 1, 1, 0. And correlating that back to the truth table, you can see that the inverse of f, where we have these products of a and b, that gives us all of our zeros. Now just looking back at the OR gate, where we had f equal to a plus b, say that f inverse is equal to a plus b, and that whole thing inversed, which using De Morgan's law would give us a inverse b inverse, or a bar b bar, which would be a 0 and a 0. So this is a pretty good tool to have in the toolbox about why it's important to expand functions. It helps with the truth table. So now we want to look at gate combinations. And to do this, we just want to consider an AND gate. So we have 2 inputs, A and B, and output F. And then we have a NOT gate, where we have F as an input and G as the output. So from this, we can simply write the output of the AND gate as A times B, and the output of the NOT gate equal to the inverse of the input, or F bar. So what happens if we tie these two together? Now the output of the AND gate is the input of the NOT gate. So we can say that G is equal to the inverse of F, which is equal to A times B, and that whole thing inversed. Let's consider a little bit more of a difficult one. And for this example, we want to express this gate combo as a function. I'm going to call that function G. So there's a few ways to think about this, but what we can do is first write out a truth table. And the brute force method would just be simply to plug in all these combinations and try to analyze this whole network of gates to see when that output is high. But we want to take a different approach. So we're going to call the output of this top gate F1 and the output of this second gate F2. So we have an OR gate here, and we have two inputs F1 and F2. So we can say that G is equal to F1 plus F2. But now we can backtrack, and we're going to look at F1. What is that equal to? Well, we have an AND gate with two inputs, X and Y. So F1 is just going to be X times Y. Now F2, we have, again, two inputs, but those are going to be the inverse of X and Y because we have these NOT gates right here. So F2 is going to be equal to X bar, Y bar. So plugging these in, we can see that G is equal to F1 plus F2, or simply equal to XY plus X bar, Y bar. Now this is a quicker method because we know that this product would correspond to 1, 1, and this product would correspond to 0, 0, and those are the only ones that we have. Now let's do the reverse of that and express a function as a combination of gates. So what we see here is that we have an OR gate in parentheses, another OR gate in parentheses, and these OR gates are tied together by multiplication. So we have an AND gate tying them together. So what we can do is have our last gate being the AND gate. That's going to be F. And those inputs are going to be equal to the output of an OR gate and an OR gate. And the inputs of those OR gates, the first one is going to be X, Y. And the inputs of the second one will be X and Z.